Today, we are going to learn more about tensors. In fact, vector is a tensor, as I told you yesterday. Let me back up a bit and introduce or revisit a couple of the slides from the end of the lecture on Monday. So you've seen this slide, but for reference, I will remind you that we defined these four space-time basis vectors. And here, this parenthesis basically tells us that these are labels. Okay, so each one of these is a basis vector, which itself has four space-time components, as enunciated here. Okay, and that is why we show the parenthesis, meaning this e parenthesis 0 doesn't mean that this is the time component of some other vector. No, this is not a component. This itself is a vector. It is labeled as a parenthetic 0. Because it is one of the four vectors. The others are labeled like this. Okay, and so these are exactly like the I hat, j hat, k hat in Euclidean geometry, but we have this fourth vector which is along the time direction at any given point. Okay, so so any vector such as our electromagnetic four vector A can be expanded in terms of these four basis vectors. And they all have unit magnitude as shown here through their component resolution. So A itself has components A0, A1, A2, A3 in this specific basis. Okay, and these bases may describe some inertial frame S, such as the hopefully static frame in which you're sitting. If there is a second inertial frame S prime, which for example has some non-zero constant velocity with respect to S, then it will have its own inherent set of basis vectors. Let's call them E alpha prime. Okay, and the components of the same vector A in this new basis, this prime basis vector, will be different, and we call them A0 prime, A1 prime, A2 prime, A3 prime. And how these components of the same vector are related to each other is determined by the relation of the frame S prime with respect to S. Okay, so we saw this slide yesterday. So this is the other slide you saw. And in the meantime, I'll remind you that if you have any questions, etc., please in the chat box write it to Shalab. Okay, not to anybody else. Otherwise, they will get missed. Okay, so to show the relation between the two frames and, for example, the components of our vector A and also the basis vectors, I choose this coordinate transformation, which is the Lorentz transformation, which you have seen in special relativity. And this Lorentz transformation is determined by one parameter, which is the relative velocity v vector, okay, this board-faced velocity of S prime with respect to the frame S. And for the simple example, I've chosen this relative velocity to be in the positive x direction. So this is the fact that the y, so remember, this is lambda yy, where lambda is this matrix, and this is lambda zz. These are unity, meaning that the x and y components of the vectors do not get mixed. They are retained as such. Okay? So the prime components are the same as the unprimed components for the y and z components. But the x and t components actually get mixed. This reminds us that this is true even with space-time intervals, such as delta t and delta x. Okay, this means that two events that are simultaneous in one frame, like if delta t is 0, it does not mean that they will remain simultaneous in the moving frame. So delta t prime can be non-zero because of this mixture. Okay, so delta t prime will then be determined by delta x, that is the spatial separation between two events in frame S, and the relative velocity between the two frames, S prime and S, which is determined by V, okay, or given by V. Similarly, the x separations will also get mixed. They will have contributions from the time separation of the two space-time events because of this lambda x 0 component. Okay, so lambda xt component. Okay, so again, using Einstein summation convention, we can describe this relation between the components of our vector A. So if in frame S, the non-moving frame, the components are given by A mu, so there will be some A0, A1, A2, A3, and they will have values in that coordinate system. Then in the S prime frame, the components of the same vector A will change to a new prime, and that is determined by this Lorentz transformation matrix. Okay, so here at any given time you will take new prime to have the same value on both sides. So for example, new prime could be the temporal component, T component, okay, or zero component. So then A0 prime will be related through lambda 0 mu and summed over mu with A mu. So A0 prime in principle will be determined by A0, A1, A2, A3 as measured in frame S. Okay. But this gives us a clue as to how we can relate the basis vectors themselves. And that clue comes from this expression. Because you know that the vector itself doesn't care who is measuring its components, right? So in the S frame, it can be expanded like A mu contracted with E mu vectors. Okay, contracted is another word for the summation convention of Einstein being an operation. So here mu again takes value 0, 1, 2, 3 in that sum. Okay, and it can alternatively be expressed as a contraction between the primed components. So A alpha prime contracted with basis vectors for the prime frame, E alpha prime. Now, if you realize, you can actually substitute out A alpha prime in terms of A mu by using equation 1. So just substitute from equation 1, the right-hand side of it, here in place of A alpha prime. So the only thing that will change is that, instead of new prime, I will keep calling it alpha prime on both sides of equation 1. Okay. And then I can take the right-hand side to the left-hand side, combine the A mu's, because I have A mu already on the left side of this equal to sign. And the right-hand side will have an A mu because of this substitution from equation 1. So this is exactly what is done here. A mu is taken common, so follow my cursor. A mu is taken common, and the remaining terms you see here come from this Lorentz transformation with nu prime replaced by alpha prime, because that is what we have here. And then one of the basis vectors is E alpha prime itself, and the other one is the basis vector on the other side. Of course, there will be a relative minus sign because you took one of these terms to the other side. But if this has to be true for any vector A, then it must be that the parenthetic quantity should vanish, which therefore gives us this relation between E mu and E alpha prime. So this relates the basis vectors in S frame with the basis vectors in the moving frame, the S prime frame. And you notice that they're also related by a Lorentz transformation matrix. But there is an interesting thing here, right? What is interesting is that this actually has the upper index summed. Okay, so alpha prime, the summation here is over the alpha prime, where alpha prime is the upper index or superscript on this lambda. Whereas in equation 1, it was a lower index that was summed. Okay, so it was mu which was summed over. So in fact, it turns out that this transformation in equation 2 is actually different from the transformation in equation 1. Okay, in fact, this is nothing but the inverse of that matrix. So objects whose components transform like this second law, equation 2, for the basis vectors, are called covariant. Okay, in an old language. In modern language, we don't use it, but they're called covariant because their components transform like the basis vectors under Lorentz transformation or under this coordinate transformation. Whereas objects whose components transform like equation 1 are used to be called contravariant. The reason it is not followed in the modern language is because, as I told you, in the modern interpretation is, and this is a better interpretation as you'll realize more and more, the vectors don't transform. Okay, the vectors are that whatever the tensors are, they don't transform. what transforms are their components. So at best, you may say, okay, this is a contravariant vector because its components transform according to a law which is opposite of the transformation law of the basis vectors. On the other hand, if you have an object whose components transform like equation 2, then those components are covariant. Okay, moving on. So we just saw an example of what we call a vector, right? Are there other types of tensor? I've been telling you that a vector is a tensor. And so let me introduce another tensor. In fact, this is a very important tensor, which we call the metric tensor. Okay, in the interest of time, again, I will not take questions, so please be patient for another 15 minutes, okay? And then, but please write in the chat box to Shalom. Okay, so what is a metric? One very, in fact, convenient way of understanding a metric is that it is a map or action that takes two vectors. Okay, I call them 4 vectors for emphasis because these are space-time vectors, and space-time indices are 4 of them. So let's take 2 vectors. A is our old friend, and let me introduce another. But A can be any generic vector. Okay, 4 space-time vector. B is another one. B, in a special case, can be A itself. But G is a map. G, the metric tensor, is a map that acts on 2 vectors A and B to produce a scalar. Okay. Here, by 4 vectors, I mean vectors whose components transform like equation 1. Okay, so that is my definition of a vector. So now, what this metric does is it acts on these 2 vectors to produce a scalar. By definition, a scalar is a quantity which does not change under coordinate transformation. Okay, a scalar is not necessarily a constant. A scalar can change from one point in space-time to another point in space-time, but its value will remain the same at that point, regardless of the coordinate system or the frame in which you measure it. That is the definition of a scalar. So mathematically, this is how it is expressed, that G, the metric tensor, acts on 2 vectors A and B to produce a quantity that is not varying with a coordinate transformation. So in component form, we write it like this. So this is something for you to memorize for now, but you will see the details in the coming slides. So this is also denoted as this inner product, A dot B. So this dot here is the same as the metric action, okay? But we know that A has components A mu, let's say B has components B mu. We saw them here, right? A mu, for example. So that means that if this quantity is a scalar, it should not have any, this whole construct should not have any free indices, because if it does have a free index, for example, if mu is uncontracted or nu is uncontracted, that means it is begging for a coordinate transformation, right? So you cannot have any free indices, which means that you can absorb these mu and nu through contractions of another indices on another index, which is what we call G. G mu nu here is defined as the components of the metric tensor. So once again, there is Einstein's summation convention implicit here. In fact, there are 2 sums because mu and nu are repeated indices up and down. There is a sum over mu going from 0 to 3, and there's a second sum over nu also going from 0 to 3. Okay, so this is invariant under coordinate transformation. In this case, specifically the Lorentz transformation we're talking about. That is why it is a scalar. So that's the definition of a metric. Let me show examples of it so that, and you will be familiar with it, so it will be easy for you to understand. Let's take the special case of the flat metric, flat spacetime metric, or the Minkowski metric. In Cartesian coordinates, in your static frame, this metric G will denote it with a special symbol, eta, where eta is the flat metric, G is a generic metric. So eta, the flat Minkowski metric, has these components in Cartesian coordinates in your inertial frame S. So eta mu nu are exactly this, meaning that eta mu nu is 0 whenever mu is not equal to nu. So for example, for all mixed indices, right, like tx or xy or zy and so on, all of those components are zeros, as you can see. Oh, by the way, it's also a symmetric matrix, okay. And it's diagonal, which means that, but diagonal with a very interesting signature. So eta tt, or equivalently eta 0, 0 is -1. And this is a convention. You could have had a different convention. Physics will not change. but I use this convention. And the eta xx, eta yy, eta zz components are all unity, as shown here. Okay. So now let us go back to the mathematical expression I had introduced on the previous slide, that if a metric acts on two vectors, it produces this scalar. So what does it mean for my flat metric? What it means is that if eta acts on two vectors, and let us call them the coordinate separation vectors, delta x, boldface, delta x, okay? By which I mean, the components of this separation are delta x mu. So basically imagine that there are two space-time points, okay? One here, another there, and they have coordinates. And the coordinate differences, like the time difference is delta t between those space-time events. And these events could be, your friend throwing a doll at you and you catching it, okay? So he threw the doll from some spatial point at some time, and you caught it at a different time at a different spatial location. So the separation in time is delta t, the separation in x is delta x, and delta y and delta z similarly for the other coordinates, right? Together we denote them as delta x mu. So this map is nothing but mu nu contracted, eta mu nu delta x mu delta x nu. If you want to expand them, then they will be exactly eta 0, 0, which is -1. That is why you have this negative sign. And then delta x 0, delta x 0, which is delta x 0 squared. Remember, all mixed indices are zeros, so only the diagonals will survive. So the next diagonal component is eta 1, 1, which is unity here in this matrix. And this will be delta x1, delta x1, so that is delta x1 squared, with that +1 here. And similarly, delta x2 squared, delta x3 squared. In most cases, there will be no ambiguity. If there is, I will clarify it. But here, this 0, 1, 2, 3 are indices. Okay, it's not that we are cubing it here. We are squaring delta x3, or equivalently, we are squaring delta z. Okay, by showing this exponent 2 outside the parenthesis. This is exactly what I've written here. So in your delta t, delta x, delta y, delta z language, this is exactly what it is. So this is also known as the line element, and this quantity, it turns out, is invariant under Lorentz transformation. So in a different coordinate system, this vector will not change because you are throwing the doll from the same point, your friend is catching it at the other point, or vice versa, right? But that separation vector does not care whether it is being measured in your playground or it is being measured in a moving car, okay, going past the playground. What changes are the components. So your some other friend in the car will measure the time separation to be delta t prime, the space separation to be delta x prime, and so on and so forth. So these individual terms will be different, but you can prove through the Lorentz transformation that this combination will actually not be different. It will be exactly the same as this interval measured in the playground frame. Okay. Maybe I'll pause here to take a question or two. Shalab, if you have any pressing questions.
So far, I don't have any question from any audience. So maybe.
All right. So therefore, you now see that, okay, so this metric is a map, and I've termed this as a tensor. And I will go to more types of tensors in a minute. But I illustrated the action of the metric with the Minkowski metric on the previous slide. So, but in general, this is what happens. This is our old expression. So this map G of two vectors onto this scalar quantity, you can parse it as follows. You can say, okay, the map is the same as this inner product. So, but A and B themselves can be written individually like this, right? You can expand A in some frame with basis vectors E mu like this in terms of A mu's, and similarly B in terms of the B nu's. I've deliberately used different symbols, mu and nu, so that I don't get confused, because this summation nu is a different sum than this one. So there is a sum here over 4 terms. There is another sum here over 4 terms, and then I've taken the dot product of those two. Okay, the dot product is a map. So, but because A mu and B nu, at any space-time point in any frame will just be numbers, you can take them outside. So that means that this basis vector will be dotted with that basis vector. Okay, so E mu dot E mu. But this is that dot product that I define as G mu nu. That's really what is happening. So A mu, B nu are those numbers from the past. And this dot product of the two basis vectors is what I call G mu nu, the components of my inner product, or equivalently the components of the metric G. Okay, and this itself will be a set of numbers, again at any given point in a given frame. Okay, like the frame S. So because these are numbers, they commute. So that is why it is okay to write it at the end or at the beginning. These are all, in each of them is a number. But of course, there is a summation over mu and u. Okay. So you know, and this quantity has to be a scalar, meaning it cannot vary from one coordinate system to another coordinate system. So one way of implying that is to say that, okay, let A mu be A mu, but this quantity, remember, nu is contracted here. The only free index is mu. So let me define this contraction of B nu with J mu nu as a new quantity B mu. Okay. And now you notice that indeed there is no free index because mu is summed over. And as we require for scalars, there cannot be a free index. Otherwise, once again, you're forced with this anomaly of what basis vector to contract it with. Okay. So this quantity is the same as A mu contracted with B mu, and the indices are up and down. That is because B with mu down is not the same as B with mu up. Okay, what is different is that to get B with mu down, you have to actually multiply with the G mu nus and then sum over nus. And remember, things can change because, as you saw, in the case of the Minkowski metric, eta mu nu is not always 1. Eta 0, 0 is -1, which means that if you may have situations where B0 is +1, but because eta 0, 0 is negative, B with index down can actually be -1. Okay, so it is important to retain these indices. That was one of the questions yesterday. That is it, meaningful for the indices to be in different places? And the answer is yes. In fact, the B mu here with mu down is not a vector component at all. So we'll come to that on the next slide or two. But before we go there, so the summary is that G mu nu can also be thought of as the inner product of E mu with E nu, or equivalently, G mu nu, these components are nothing but the map with the same metric tensor of these two basis vectors. Okay. And equation 3 reminds us that, if you take away one of the basis vectors, so keep it unfit, then G acting on only one of the vectors B is the same thing as G mu nu contracted with B nu and mu left uncontracted. So that you can actually contract mu with another vector like A. But here it is left uncontracted. So that is what creates this quantity B with mu down. Okay, that's consistent with equation 3. Let me go over this slide, and then I'll take some questions. So you better submit your questions to Shalak. So in fact, this B mu, it turns out these are the components of not a vector, but a dual vector. Okay, it's different from a vector. The reason it is different from a vector is because the dual vector has a different transformation law. Okay, in other words, the components of the dual vector do not transform like the components of a vector. So they do not transform like equation 1. Okay, so they do not transform contravariantly. In fact, we'll find that B with mu down, right, those components actually transform like this basis vector transformation law. So that is why sometimes some people call them covariantly transforming components. So covariantly transforming components, B mu. So in fact, so let us introduce them. When there is only a single index, they're related to one forms, but that's a technical term that I'm not going to go into details on. So, but I can introduce these dual vectors as follows. I can ask, okay, can there be a map that takes a vector to a scalar? Remember, this is a different question from the question on the metric. Metric was a map that took two vectors to a scalar. So now I'm saying, can we have a new map that takes only one vector to a scalar? And the answer to that question is yes, it is a dual vector. So we have already used up the symbol G for the metric. So now let me introduce the symbol P. I use a tilde because it is not a vector. Okay, it is not like the vector A. But what does P tilde do? P tilde acts on a vector like our vector A to produce a scalar. Okay, it's the same A mu P mu, just like we had A mu B mu here. Okay, so the idea is the following: when P, the dual vector, acts on a vector A, the action can be defined as follows: P, you replace A with its expansion in frame S, as A mu contracted with the basis vectors E mu. But again, at any given space-time point, the A mu's are numbers, so they can be taken out. This dual vector therefore acts on these basis vectors like this. And again, there is a contraction over mu. So there is a sum over mu here also. That sum is retained. Okay, now P acting on this, that is what is defined as the components of the dual vector P mu. Okay. So this is reminiscent of what we did with A also. Okay. So A was expanded in terms of components. Here, P acting on the basis vectors give us the components of P, which are P mu. This is reminiscent of the metric tensor as well. The metric tensor acting on these two basis vectors actually give us the components of the metric tensor, G mu. Okay, so there again, the language is very similar. So a dual vector is also called a 0-1 tensor. The one down denotes that its components have a subscript. It has no superscript. Okay, the A vector can therefore be termed as a 1-0 tensor. Okay, where 1 instead of this 0 denotes that it has a superscript, and so 1-0. The 0 down means A has no subscript. So I've not written it. Oh, this is where I've written. So a vector is a 1-0 tensor. See at the bottom, a vector is a 1-0 tensor. Okay, just like our vector A. The dual vectors P tildes are 0-1 tensors. A metric will be what kind of a tensor? It will be a 0-2 tensor because its components have two subscripts, mu and mu. Okay. Another way of saying that is that a metric takes two vectors to a scalar. So the fact that it takes two vectors is denoted by this 2 down here. And similarly, a dual vector takes a vector to a scalar. So the fact that it takes a vector, one vector, is denoted by this 1. Just like we expanded the vector A in terms of basis vectors, therefore you can ask, can dual vectors, arbitrary dual vectors, be expanded in terms of basis dual vectors? And the answer is yes. So the idea is the same. We just call these omega tildes the basis dual vectors. Their components are again those 1, 0, 0, 0, 0, 1, 0, and so on and so forth, except that I define the basis vectors, the dual vector, I define the dual vector P tilde as an expansion or as a resolution in terms of these basis dual vectors, and the components are P beta. These are the same components as the P mu here, as you can see as follows. So P tilde acting on a basis vector is the same as this contraction acting on that basis vector. So I substituted P tilde with P beta omega tilde beta, but again at a point P betas are just numbers. So this means that this is just a summation, weighted sum, okay, with P tilde being the weights, or P betas being the weights. Omega tilde, the dual vector, acts on the vector, but if I've defined this as these numbers P mu, then this quantity has to be P mu, which means that omega tilde acting on E mu should be this Kronecker delta beta mu, which means this is only 1 when beta is equal to mu, otherwise it is 0. And this contraction over beta means that this Kronecker delta contracted with P beta has to be just P mu, where mu is the free index. Okay, this is exactly what we used here. So this all squares up. It's all consistent. But then you may ask, but there has to be a symmetry. If you say that a dual vector acts on a vector to give a scalar, then can a vector act on a dual vector to give a scalar? And the answer is yes. A vector A can act on the dual vector P tilde to give a scalar, and it is as follows. So now I replace the P tilde in the parentheses or in the argument in terms of this expansion. Okay, this is the same expansion. Don't be confused by the mu. Remember, beta here is a dummy index, like your integration variable. Let's say the y variable integrated out, right? So here beta is a dummy index. It's summed over. So I might as well write this as P mu in contracted with omega tilde mu. In either case, there is a summation over mu or beta here from 0 to 3. Okay. So A acts on this. Once again, P mu's are numbers, so they can be, so the action of A is really on the dual vectors. And so this, by symmetry, you define so this is the definition of the component of A. So A acting on a basis dual vector omega tilde mu actually gives us, by definition, the component of A, which is A mu. And then once again, you notice that this is the same scalar quantity as we wrote in equation 1. So this is consistent. A takes a dual vector to a scalar, and it's the same scalar as you get by acting the dual vector P on A. Okay? So in this sense, indeed, A is a 1-0 tensor. It's a 1-0 tensor because it acts on the dual vector and nothing else to take to a scalar. So we introduced a 1-0 tensor, which is a vector. We introduced a 0-1 tensor, which is a dual vector. We introduced a 0-2 tensor, which is a metric tensor, right? There are other types of 0-2 tensors also, like the T mu nu, the stress energy momentum tensor I showed you yesterday. So in general, the tensors can be M-N tensors, where an M-N tensor will act on how many vectors? It will act on N vectors and M dual vectors to take to a scalar. Okay? So that's a map. So M-N tensor is a map that takes N vectors and M dual vectors to a scalar. Scalar meaning a quantity that remains invariant under coordinate transformation. Okay, I will pause here to take questions. So let me see if anybody has.
Yeah, there are a lot of questions actually.
Okay.
Okay, so one question is, actually, I think people are confused with your signature convention, minus plus plus plus. So one question I got was, can we take T to be positive and others to be negative? So I think they're confused between the components of a vector and the matrix signature.
They want to take what to be positive?
So the TT component of eta mu nu is negative and
Yeah.
rest all are positive.
Yes.
So
The opposite?
So yeah, one question which I got was like, can we take the time coordinate to be positive and all other coordinates negative? So what I think is that,
Yeah, that is a different signature convention. As I already answered that question, right? If you
Yeah.
consistently use your metrics so that this is positive and those are negative, physics will not change. See, this comes from the fact that this comes from one of the postulates of special relativity, right? That the speed of light is constant in all inertial frames. So in fact, if you, here actually I'm setting c equal to 1. Okay. Strictly speaking, there should be a negative c square, delta t square. Okay. And that is when all the dimensions will be spatial. So I have set c equal to 1. But the point is that this quantity remaining invariant under coordinate transformation essentially means that the speed of light is unchanging in any system. And that statement that the speed of light remains unchanged is respected even if you flip the sign so that this is positive and the other spatial coordinate signatures are negative. So that statement will remain unchanged. So there is no physics lost or changed by just this sign change.
Mm-hmm.
So just become comfortable with it. This is totally correct as long as you consistently follow it everywhere. But there are textbooks that do the opposite, and that's also correct as long as you don't mix them up. What other questions do you have?
So one question was how to draw four vectors diagrammatically.
Most people can think about them in their own head. No, I'm just joking. So most people, they just think of them at most in 3 dimensions. Okay, they suppress the 4th dimension, and that's totally fine. Oftentimes that is easily done, as I showed you on yesterday. You can just imagine. In fact, oftentimes people suppress 2 of the dimensions. Okay, they may suppress the z dimension and the t dimension, and you can just imagine that. Let's say you choose your action, okay, your phenomena to. You don't have to limit it this way, but you start imagining in simpler cases, and then you generalize. But you can imagine that, okay, your whatever phenomenon you're studying is limited to, let's say, x and y plane, and for example, 2 neutron stars orbiting around each other. Okay, and that is indeed mostly limited on a plane. And as they come closer, because they're losing energy to gravitational waves, something is changing in time. The distance of separation is changing in time. So you portray that with lots of slices, lots of X, Y slices stacked vertically, where the vertical axis moving up is the positive time direction. Okay, so time is moving vertically up. So oftentimes we imagine things like that, but if you have to go beyond it, then yeah, that is where mathematics can be useful, where we can use the help of mathematics to understand how other components are behaving as this evolution takes place. What else?
So some people were asking again, what is the difference between covariant and contravariant vectors? And looking only at the vector, how can we tell whether it is covariant vector, contravariant vector?
Yeah. The answer is yeah. Please stop using that language. What you call contravariant vector, I'll just call them as vectors. Okay, and that is because, as I said, what really is varying or not varying according to the Lorentz transformation are their components. Okay, as I showed here. Okay, it's the components that are varying or transforming, like in this red box. The vector itself remains unchanged. So what determines whether it's a vector is whether its components actually are varying according to this law or this inverse law. Okay, here remember the upper index is contracted, not the lower. And objects whose components transform like this blue box in equation 2 are called dual vectors according to me and according to most modern texts. And at best, we'll say that their components actually obey this covariant law. Covariant meaning the components vary in step with or in sync with the way these basis vectors transform. Okay, so that is why they're called covariant. Mm-hmm. How can we tell? The best way to tell them is to understand, their properties. What will they do when they act on other vectors or other dual vectors? And I'm going to come to those examples in a minute. So let me move on. I'll take, again, questions at the end. So do write in the chat box. So let me give you some examples to, again, clarify what's a vector and what's a dual vector. So the space-time interval, okay, delta x, this is a vector. It doesn't care what coordinate system you're expressing its components. But let's say in the S coordinate system, right, its components are, this time separation between two events, like, somebody throwing a ball and you catching it. This is the X separation between those two events, the Y separation, the Z separation, right? This is a vector. The reason it's a vector is we know that because, for example, the metric will act on it and another copy of it to take to a scalar. So that is one way you know it's a vector. But another way is that under Lorentz transformation, the space-time separation components transform like that red equation, equation 1. And that's a contravariant way of transforming. Okay, so that is why we know this is a vector. Another vector is the four-velocity vector, where you take the derivative of coordinate separations, right? The coordinate x with respect to the proper time. Proper time is the time measured by the clock of the mover himself or herself. So d tau by definition is a scalar. It doesn't change because it is the time measured in a specific frame. Its value will be the same in all frames. So therefore, because dx, remember dx is nothing but delta x in the limit that dt is tending to 0, right? So because this quantity is a vector v, which is just the division of this quantity with the proper time in the limit that this proper time change is going to 0, right? This quantity also has to transform like vectors, meaning it is a vector. Its components transform like vector components. The components are like this. Once again, dt here is throughout a scalar, and because the numerator transforms like contravariantly, so therefore this is a vector. The four velocity is a vector. Similarly, the four momentum is a vector because four momentum is nothing but another scalar multiplied with the velocity, four velocity vector, right? M here is the rest mass of a particle, and the rest mass by definition is again unchanging. So therefore, the components of P transform like the components of any vector, okay, according to the coordinate transformation or the Lorentz transformation for a specific example. Dual vector example would be the gradient of a scalar field. So for example, how the density of air, okay, there I have to be careful. There has to be a better example, but let me just say, okay, how some scalar field is changing from one point in your room to another point. to in component form. To study that, you will take the derivative of that scalar field with respect to time, because it may change with time. You will take its derivative with respect to x, and then y, then z. And now you notice that by definition, phi doesn't change, right? It's a scalar field. But the denominator now has quantities which are components of a vector, but they're in the denominator. So that transformation law is actually covariant. Okay, you can prove that because this is a down index, a downstairs index, like the basis vector index is downstairs index. Therefore, those components transform like this. Remember, here the prime is actually on the right-hand side. There, the prime was on the left-hand side. That is why I keep saying that this lambda alpha prime mu, I mean, you have to, if you take it to the other side, you know, that will be an inverse transformation compared to this. Okay, so this transformation, for example, takes you from one frame to another frame with a velocity v in the positive x direction. If you move this lambda to the left-hand side, so that the prime is on left alone on one side, just like the prime is left alone on one side here, then that will be the inverse transformation that will bring you back from that moving frame S prime to the old frame S. Okay, so that is why this is the inverse transformation. So components that transform like this are covariant and their indices are down. So that is exactly what's happening here. Its components can be written as, you know, d phi dx mu, but mu is down, and therefore this quantity, these components transform covariantly. Okay, they transform like the basis vector, and that is why the gradient of a scalar field is not a vector. It's not a vector because its components transform not like the components of a vector. So in Euclidean geometry, it doesn't matter. So people often say gradient is a vector, but it is not a vector. It's actually a dual vector. So keep this distinction in mind. And now perhaps you understand this. The purpose of it is important because the transformation law is different. Once again, you know, eta 0, 0 being negative actually will change things depending on how you're transforming. So the vector normal to a surface is again, you know, it's not a vector, it's actually a dual vector. So this is old language, it's a misleading language. And that is because a surface is specified by a function of the coordinates, and the normal is nothing but the gradient of that function. And the gradient by definition is a dual vector. Okay, so think of more examples of vectors and dual vectors. That's your assignment. So, and then I have a couple of other questions. You know, we worked out how the basis vectors, the E alphas, transform under Lorentz transformation, right? That is the covariant law, which I showed in the blue box in equation 2. Figure out how the dual basis vectors, omega tilde, will transform under that law. And the hint is that, you know, this index is up, so its transformation law should be the same as the transformation law for the components of vectors, okay, what you call contravariant components. Another question is energy a scalar under Lorentz transformation? The hint is no, it is not. Just like, you know, the electric potential A0, also called phi by some people, you know, oftentimes it is called the scalar potential, but it's not a scalar. It's actually the time component of this electromagnetic 4 vector. Energy, perhaps by now you have recalled the answer, is just the 0th component of the 4 momentum vector, right? So it is the 0th component of 4 momentum vector. So energy is just this rest mass m times dx0 by d tau, which is just dt by d tau, where t is the coordinate time and tau is the proper time. In the rest frame of your clock, the change in time t is the same as the proper time, because t is just the proper time in the rest frame of the clock. And so then the energy is just the rest mass m. And here again, I'm actually suppressing c. The rest energy should really be mc squared. So, okay. So that is why I'm setting c equal to 1 here. But if you're measuring that clock in some other frame, then your t coordinate is not the same as the tau coordinate, and you will pick up the boost parameter, because dt by d tau is the boost parameter gamma, which I had introduced in the Lorentz transformation. So then you will notice that the energy now becomes the rest mass of the clock m times gamma. Okay, of course, times c squared. But so now you notice that the energy does change from one frame to the other, right? In this case, it acquired the boost parameter gamma. So energy is not a scalar. Okay, let me next go to do some calculus. We want to do calculus because if you want to measure the curvature of a surface, you have to know how the vectors actually change as they are translated from one point on that curved manifold or curved surface to another point. So here, let us ask what would be the derivative of my vector v. Okay, this is the same type of vector as vector a or b I introduced earlier. Okay. But if you take the vector v, coordinate derivative of it with respect to x nu, okay, then notice that v itself is an expansion, right, of numbers like v mu's and the basis vectors, where mu here is contracted. Okay, nu, therefore, I've maintained it as a separate symbol. Okay, I was getting thirsty. So what you do now is that you realize that, okay, I have to differentiate by parts. So first, this derivative with respect to the coordinate x nu will act on the components v mu. Remember, I said that these are numbers, but these are numbers at any given space-time point. But across space-time points, v mu can change. Okay, so in that sense, they are functions, okay, of space-time coordinates. So this derivative will not necessarily be zero. But then when I'm differentiating a part, the second term will be one where v mu is a spectator, but the derivative acts on the basis vectors. Now, in Cartesian coordinates, in Euclidean geometry, the derivatives of all these basis vectors, like I hat, j hat, k hat, they're zero. So we never bother about this second term. And we just leave after we have calculated this first term. Okay. But in curvilinear coordinates, like r coordinate, theta coordinate, phi in spherical polar, the basis vectors can change with let's say x, y, z, or even r, theta, phi. Okay. But when the manifold is curved, there also the basis vectors can change from one point to another point. So this part cannot be ignored in general. Okay. But what is this part? The thing is, the important insight to remember is that the change of a vector is a vector itself. Okay. So all of these quantities for fixed nu, that is, okay, can be expanded in terms of the basis vectors in that space or in that space-time. Meaning, suppose you're given some fixed mu and some fixed nu. So mu could be zero, nu could also be zero, right? Then the derivative of E0, this basis vector with respect to time, x0, the claim is that that should be expandable in terms of the basis vectors themselves, that is E0, E1, E2, E3. The expansion coefficients can be interesting depending on the basis vectors themselves and the coordinate with respect to which you're taking the derivative. Okay, so for example, if these are the r hat, theta hat, phi hat basis vectors, and if this is the derivative with respect to x, then indeed that these basis vectors actually will change with respect to x. And so gamma, alpha, say r and x, I mean, these will be interesting. Typically, you would want these derivatives to be in the same coordinate system. So you will take the derivative of, say, ER with respect to r, the radial coordinate. So then this will be gamma alpha RR, E alpha, with alpha summed over. Okay, and but the main insight is that this derivative of a vector is just a linear expansion over the basis vectors themselves, and these gammas are just expansion coefficients, the weight factors. Given a mu nu, this is a sum over the alphas, so 0, 1, 2, 3. If you change mu nu, you can get other coefficients, okay, other numbers, and these are called Christoffel symbols. So using this now, I can go back and ask, okay, how can I then expand this derivative of vector in terms of the ordinary derivative of the vector components, v mu's, and the Christoffel symbols. So all you need to do is you substitute this blue box for this basis vector derivative in the red box equation 1, and then combine terms. So then the derivative of a vector v with respect to the coordinate, okay, the original term remains, and here I've substituted for this Christoffel symbol expansion, the gamma expansion, and then I combine terms, which I will leave it for you to figure out later. But at the end of the day, you will find that you will get this ordinary derivative, but also these Christoffel symbols, like in this basis. in this curly brackets, you notice that the bold-faced vector derivative can be written in terms of the component derivatives, and also the Christoffel symbols contracted with the components themselves. And E mu is comes out as a common factor. So this is beautiful. This tells us that so I can express the derivative, the coordinate derivative of a vector v bold-faced as a linear expansion in terms of the basis vectors themselves. That is what has happened here. Okay. So this curly bracket terms are then grouped as a new derivative, which is called the covariant derivative, or v mu semicolon mu. Okay. This is different from comma nu or this symbol derivative. Okay. Partial x nu. So the covariant derivative, that is the derivative of v mu, the components, semicolon nu, is defined in terms of the ordinary derivative v mu comma nu, which is nothing but this ordinary derivative here. So that is partial v mu by partial x nu. Okay, that's what I'm calling v mu comma nu. Okay, that ordinary derivative plus this term containing the Christoffel symbols. Okay, contracted in beta. So what we have found is that, okay, if you take a vector and take its coordinate derivative, it is nothing but this covariant derivative components v mu semicolon nu, which can be computed like this in terms of ordinary derivatives and Christoffel symbols, contracted with the basis vectors E mu as shown in equation 2. Okay, so these Christoffel symbols can be computed by realizing that we actually have a freedom in defining these Christoffel symbols. The choice I will make is one where when you contract two a vector with a one form, right? Or when you contract two vectors using the metric tensor, then you can ask the same question: what happens when I take the derivative of that contraction? So let me go back. So I'm going to take x nu derivative, but let me go back to the metric, like here. So you can ask what happens when I take the derivative of this quantity with x nu, which means that you have to take the derivative of these components with x nu. Now you know what you will get when you take the derivative of a mu and b nu, but what if you take the derivative of g mu nu? So that is where I'm going to say that I want that covariant derivatives to be such so that its action on g mu nu is 0. Okay? So that it basically just acts on the vector components. So such derivatives are called derivatives that are metric compatible, and they then impose on us some restrictions on the Christoffel symbols. So basically, this is what I'm going to do. I'm going to say, let me introduce one more symbol. This is where I missed the chalkboard. So I'm going to introduce all the symbols simply because books do it, and it's important for you to be familiar with them. The ordinary derivative is written like comma nu, but also sometimes written as partial nu, v mu. But the covariant derivative is written with a nabla subscript nu. Okay, so this semicolon nu is also sometimes written as a nabla. That's an inverted delta sign. Okay, subscript nu acting on v mu. So this is what we are going to do. We are going to say that this is what I was talking about. This is that nabla subscript mu. Okay, this is a covariant derivative. You might as well have said that, okay, I want this covariant derivative to act on v mu. Okay, in that case, of course, instead of mu, you will be saying mu. And indeed, you can also contract over mu. But here, so the choice I'm making is that I'm saying that let my metric derivatives, the covariant derivatives be compatible, metric compatible, which means that their action on g alpha beta is equal to 0. Okay, this will help in taking derivatives of scalar quantities, as we see in the next slide. But the moment you require that the covariant derivatives obey this property, you can show that the Christoffel symbols then can be expressed as ordinary derivatives, single derivatives of the metric itself. Okay, this comes basically from a definition like this. Remember that this has the covariant derivative acting on it, and the covariant derivative acting on the metric, if it is 0, that has implications on the Christoffel symbol properties. Okay, so I'm asking you to take this on faith right now. This will become clearer in the next few slides. But the point is that requiring the covariant derivatives action on the metric to be 0 means that the Christoffel symbol can be computed in terms of metric derivatives like this. So now we have a prescription. The prescription is that if you're given a space-time, okay, whose metric is provided to you, and remember, this is what happens in the flat space-time case, right? In the case of the flat space-time, you're given the Minkowski metric, okay? Then from taking the derivatives of the Minkowski metric components, you can get the Christoffel symbol. And once you know the Christoffel symbols, you can find the covariant derivative of any vector in flat space-time. And the answer is trivial, because in Minkowski spacetime, in Cartesian coordinates, okay, all of the metric components are zeros or ones or negative ones. So they're constant. So the Christoffel symbols all vanish. And if the Christoffel symbols vanish, then the covariant derivative of any vector is just the same as the ordinary derivative. But things become interesting even in flat spacetime itself. But if instead of Cartesian coordinates, you use spherical polar coordinates, okay, there the metric components are not constants, right? You can have metric, so GRR will be unity, but G theta theta is R square, G phi phi is R square sine square theta. So now you notice that the metric coefficients depend on the coordinates like R and theta, which means that the coordinate derivatives with respect to radius or theta will be non-zero. So in general, the Christoffel symbols are not zero even in flat spacetime, but in Cartesian coordinates. And in curved spacetime, of course, they're in general not zero. So which means that the covariant derivative of a vector is not zero. This derivative, is not just the ordinary derivative. Okay, it has other contributions. That is what I should have said. And in fact, these contributions will actually help us define curvature of spacetime. Okay, I have, I think, 1 more minute. So let me show you one more property and then we will end. So this is the definition of covariant derivative of a vector. You understand that it is the ordinary derivative and a term containing the Christoffel symbol. But you can ask, what is the covariant derivative of a dual vector, right? And to answer that, now you bring in the scalar product. You notice that V mu contracted with P mu is a scalar, right? We saw this when we dealt with the action of a metric, right? Here, for example, or interestingly here, I mean, this is a scalar. P takes A to a scalar quantity. So V mu P mu is a scalar, which means that it does not get expanded in terms of basis vectors or dual vectors. So its covariant derivative will have no vectors to act on, no basis vectors to act on, which means the covariant derivative of a scalar, this semicolon mu, right, is nothing but this ordinary derivative, common. So common means you're taking the derivative of this parenthetic quantity with respect to x mu. Okay, that is what this is. So this can be differentiated by parts. So the first term is when d by dx mu acts on v mu. I should say del by del x mu acts on v mu. And the second term is when this ordinary derivative acts on p mu. Okay, but this this ordinary derivative of the vector components can be expanded in terms of the covariant derivative minus this Christoffel symbol, right? All I'm doing is I'm going back to this definition and I'm expressing this ordinary derivative in terms of the covariant derivative of the components minus this Christoffel symbol piece. Okay, that is all I have done here. And when you do that, you realize that you can now you can take the v's common, okay, and you get an expression like this. So to do this, you'll have to rearrange your terms a bit. But once you do the rearrangement, I'll let you figure that out. You can prove that the covariant derivative of P mu is the ordinary derivative minus this piece. Okay, essentially, yeah, minus the Christoffel symbol P. So this brown boxed expression is again very similar to equation 1 with 2 changes. One is that the mu index is all down because it's a covariant index, right? And the Christoffel symbol has a negative sign. Also, in equation 1, it is this beta index on the Christoffel symbol which was contracted, but now that index is actually an upper index. So remember these definitions. So because now you can generalize to any tensor. So if you have a tensor T alpha beta, okay, this is a 2-0 tensor, right? The covariant derivative of this, and this is the same thing as T alpha beta semicolon mu, is the ordinary derivative with respect to mu. And now for each of these symbols, you will actually have a Christoffel symbol term. So there are two terms. One where beta is a spectator, meaning it just stays on T alpha beta. Alpha is like the index mu here on the vector. So it will generate this kind of a term, okay, where instead of mu, you will have alpha. And that is exactly what you have. Gamma alpha P mu, T nu beta. So here the contracted index is nu, the free index is beta. Beta index is a spectator. Okay, and in the last term, you will have alpha as the spectator index on T, and beta is now the index with respect to which I do the contraction. So the second index is where I am using mu. The upper index on gamma now acquires that free beta. Remember, the number of free indices has to be the same, and their characters have to be the same as well. So alpha, beta remain the free upper indices everywhere. In this term, here in the gamma and the T, and here again in the gamma and the T. Okay, and finally, similarly, you can define the covariant derivative or deduce the covariant derivative of this 0-2 tensor components, P alpha beta. It is just the ordinary derivative, and then again minus from the brown box here, gamma P minus gamma P, where in the first case, this beta index, the second index is a spectator, the contraction is over its first index with the Christoffel symbol. And in the second term, you have the first index alpha as a spectator, and the contraction is over the second index nu with the Christoffel symbol. Okay, so let me stop here, and this is the end of the first lecture today. I have one more lecture in half an hour, but yeah, I can take questions now.
So yeah, one question is, in your definition of dual vector, you took the coordinate mu out. So how did you take it?
Yeah, so take it as a definition that ultimately gives us consistency. As I showed later, that the same thing happens when you act the vector on this dual vector. But the basic sentiment is the following: that P, these actions. Yeah, again, I don't have a chalkboard, so it's a bit difficult. But so just bear me up. What's happening is the following: these obey this linearity law, where P acting on alpha A plus beta B is the same as alpha times P acting on A, where alpha is a scalar, plus beta being a scalar, times P acting on B. Okay, so imagine that instead of A, I have a linear sum of vectors. Okay, the linear sum is alpha A plus beta B, where alpha and beta are scalars. Okay, so then this action of P on that linear combination of vectors is the same thing as alpha times P tilde acting on A plus beta times P tilde acting on B. Okay, so here I'm using the same law here. This is just this a linear sum of 4 basis vectors. So, and therefore the answer is that this action is the same as, this scalar like A0 with P times P acting on E0 plus the scalar A1 times P tilde acting on E1, and similarly for 2 and 3. And that's the same thing as writing it this way. Okay? So this is just the definition of how P tilde will act on a vector or a linear sum of vectors. That's exactly how this is defined.
So another question is, you defined the metric G mu to be a mapping from something to something. So one question was, what is that mapping from? So from what to what is this mapping?
Yeah. The space. So when you say from what to what, there are 2 spaces we are dealing with, right? The first is the space on which the map acts, and that is the space of all vectors. A and B are just 2 example vectors on that space. And the second entity is the space to which this action takes the object, right? And that space is a space of scalars. So G acts on the space of vectors, and the result of its action gives a scalar output. Okay, so this is a scalar quantity. Again, at any specific space-time point, this is a number, but across space-time points, that number can change. So then it is just a scalar function. What else?
So, another question is, you defined dot product between 4 vectors. So one question was, like, when we do it with 3 vectors, we take the angle between them, cos theta. So can we do a similar way or not? Here
Yeah, that is the cos theta is a specific example of this. Okay, in fact, cos theta is nothing but a component of the metric. So, for example, if these are all Euclidean vectors, okay, so suppose I'm not in 4-dimensional space-time, but I'm just in this imaginary 3-dimensional Euclidean space, right? Then A and B are vectors in the space, and I, J, K are unit vectors in that space. So indeed, you can have 2 vectors, and just and these vectors could indeed be I, J, K. So these will just be I dot J, J dot K, and I dot I, and that kind of thing. So in general, this sum will involve all of those, and some of them will be the cosine of the angle between, will ultimately give an answer which will be which can be re-expressed as scalar numbers times the cosine of the angle between 2 unit vectors along these 2 arbitrary vectors, right? So that cosine is just another way of capturing information in this dot product. Right? The cosine of the angle is nothing but the cosine of the angle between these 2 vectors. So that cosine of the angle is actually related to this expansion. I mean, you just go back and rework it in terms of Euclidean geometry, and I think that will help your intuition about them a lot.
So another question is, why did we take the index position of the vectors and dual vectors opposite, like one above, one below?
Oh, because they are opposite, right? I mean, I demonstrated this through this example, that there are certain objects which are naturally dual vectors and not vectors. That is because, indeed, I mean, this is an obvious example. I mean, the derivative of a scalar, the coordinate derivative of a scalar obviously has indices downstairs. And it is important to classify it like that. So the components here will be like D, forget about the tilde, because tilde denotes that it's a dual vector, but the components will be like, D with mu down phi, okay? So D mu phi will naturally have a coordinate transformation law that is like equation 2 here, because even the basis vectors, therefore deliberately, in anticipation of this, were chosen to have their indices downstairs. But it all becomes so consistent in, like the vector expansion, that yes, this is this transformation is the opposite of this transformation in the red box, right? And that is exactly how they transform. If you ask how the gradient transforms, the gradient of a scalar field actually transforms like this law, not like that law. So I cannot, if you make the mistake of treating the gradient as a vector, then you will get wrong answers, because they will actually, you will be implementing the wrong transformation law. You will be computing the components of the gradient incorrectly in the S prime frame, in the moving frame.
Yeah.
And it all comes from here. That is because, these dx mu's are actually down, not up, as in a vector.
And one question is the Christoffel symbol a tensor? And what is the significance of covariant derivatives?
Yeah, the significance of covariant derivative I'm going to come to in the next lecture, so just be patient. They will allow me to define curvature. Okay, they will also allow me to define parallel transport. That is, how do I remember in flat space? It is easy to say, okay, the vector here is the same as the vector there, because from Euclidean axioms, you know that you know how to define parallel lines. Okay, but on curved space, to define whether a vector is changing as you take it from one point on the curve to another point on the curve, you have to be able to define whether you're keeping the vector parallel to itself or not, which means you have to measure changes in the vector. Measuring changes in a vector in curvilinear coordinates or in curved spaces or space-times requires that we allow for the basis vector itself to change. And that is where covariant derivatives come in. So we'll talk exactly about that in the next lecture. Sorry, what was the previous question?
Is the Christoffel symbol a tensor?
Yeah. Okay, the Christoffel symbol, you can view it as a tensor, okay? But to view it as a tensor, you will have to fix these mu and nu. The idea is that you will have to, as I was doing, I was taking these as labels, right? I was saying that, okay, mu and nu, once you ask, okay, how this derivative, it can be expressed in terms of basis vectors, it can be done through this Christoffel symbol expansions. So once you fix mu and nu, then alpha is the summed over index. So then indeed you can think of them as components of a tensor, okay? But if you lose track of that, then it is best not to think of them as tensors, because, for example, if you ask what happens to these components under coordinate transformation, then you'll find that the coordinate transformation is not like the Lorentz transformation I showed, and you have mixture terms. So it really depends on if you are being very careful, you can actually treat them as tensors, and you'll be totally fine. But if you're not careful, you'll get mixed terms, and so you will see books where they say that the transformation law is not like that of tensors.
Mm-hmm.
So operationally, maybe if you're careful, just be aware that under coordinate transformations, depending on how you're treating these different indices, you will get terms which are inconsistent with coordinate transformation law of tensor components.
Mm-hmm. And many people were asking if they can get the slides.
Yeah, so and the answer is yes. How do I make the slides available? I think like Professor Seem Paranjpe or somebody who is organizing these lectures can communicate the slides to you. They can make them available on the website from which you can download. Maybe that will be the easiest instead of emailing everybody. Although emailing is also possible. Mm-hmm. So I will certainly make them available, and I think sometime this week you should be able to get an email on how to access them.
Sure. So next lecture will start within 15 minutes. So it is 9:15. So
let us all get a coffee break or something.
Yeah,
I know
sure.
it's to a coffee shop, but maybe we can have it in there. So see you in 15 minutes.